Hello students, welcome back to next session. So where we are continuing the same topic, psychrometric of air conditioning processes. Now we are going to see the next part. As I said earlier, I have divided this into three parts. Now we are commencing part 2, and we have one more part, that is part C, that we will see in next session, and we will see a few more processes, air conditioning processes here. So these are the topics, and now we are seeing the psychrometric of air conditioning processes next part. So same topic only. So these are the air conditioning processes we are dealing here, and now we have completed sensible heating, sensible cooling. Now we are starting the humidification and dehumidification. We will see cooling of adiabatic humidification, cooling of humidification by water injection. So these three processes we will see in this part. So in next part we will see heating and humidification, humidification by steam injection, adiabatic chemical dehumidification, and then in next session we will see adiabatic mixing of air streams. So humidification and dehumidification. So here the addition of moisture to the air without changing its dry bulb temperature. So without changing dry bulb temperature, addition of moisture to the air is known as humidification. Similarly, removal of moisture from the air without changing dry bulb temperature, so that is known as dehumidification. Heat added during humidification process and heat removed during dehumidification process is shown on the psychrometric chart, so that I will show you. So observation on psychrometric chart. So in humidification, relative humidity increases from 5.1 to 5.2, and specific humidity also increases from W1 to W2, and dehumidification, in the dehumidification the relative humidity decreases from pi1 to pi2, and specific humidity decreases from W1 to W2. So change in enthalpy in humidification, change in enthalpy is shown by the intercept H2 minus H1 on the psychrometric chart. Since dry bulb temperature remains constant during humidification, sensible heat also remains constant. The change in enthalpy per kg of dry air is caused during increased moisture content equal to W1 minus W2 kg per kg of dry air. So this latent heat transfer, that is TA. So now this is the humidification process. So from 1 to 2 it increases, the specific humidity increasing from W1 to W2, whereas in dehumidification from 1 to 2, so it decreases, the specific humidity is decreasing from 1 to 2. So here it is a rising process in specific humidity, it is here the decreasing process in specific humidity. So this is only difference in these two processes. In dehumidification, the above equation may be written as LH equal to H1 minus H2, that is equal to HF W1 minus W2. So absolute humidification and dehumidification processes are rare in practice. They are also accompanied by heating or cooling. So in air conditioning, the latent heat load per minute is given by, so LH latent heat is equal to MA delta H equal to MA HF delta W. So that is V rho HF delta W, where MA equal to V rho. So V is the rate of dry air flowing in meter cube per minute. So that is rho is density of moist air. So that is taken as 1.2 kg per meter cube of dry air. HF equal to latent heat of vaporization, so that is 2500 kilojoules per kg, and delta W equal to difference in specific humidity between entering and leaving conditions. So W2 minus W1 for humidification, or W1 minus W2 for dehumidification. So please remember this, and substituting these values, latent heat equal to V into 1.2 into 2500 into delta W, so that is equal to 3000 into V into delta W, that is kg kilojoules per minute, so that is equal to 3000 into V into delta W divided by 60, so that is kilojoules per second. So that is equal to 50 into V into delta W, so that becomes kilojoules per second, so that is also known as kilowatt. So humidification methods. So there are a few types that we will see here. Air washer humidification. The humidification is achieved by supplying or spraying steam, hot water or cold water into the air. So humidification, just spraying water in air, so there the air becomes humid. So that is a very simple technique. And humidification can be obtained by two methods. One is direct method. And this method, water is sprayed in a highly atomized state into the room to be air conditioned, and this method is not very effective, it is not used also. And indirect method, water is introduced into the air in air conditioning plant with the help of an air washer. So this is the air washer humidification. So this conditioned air is then supplied to the room to be air conditioned. So air washer humidification, the air washer humidification may be accomplished in three ways: by using recirculated spray water without prior heating of air, by preheating the air and then washing it with the recirculated water, by using heated spray water. So these are the three ways we can achieve the humidification using air washer humidification method. So dehumidification may be accomplished with the help of air washer or using chemicals. In the air washer system, the air is cooled below its dew point temperature so that it loses moisture by condensation. So chemical dehumidification, air is passed over chemicals which have capacity to absorb moisture. So typical chemicals used are absorbents like silica gel and activated alumina. Sensible heat factor, that is known as SHF. As a matter of fact, the heat added during a psychrometric process may be split into sensible heat and latent heat. The ratio of the sensible heat to the total heat is known as sensible heat factor. So it is briefly written as SHF or sensible heat ratio. So SHR. So anyway it can be represented. So mathematically SHF equal to SH divided by SH plus LH. SH is sensible heat, LH is latent heat, and the sensible heat factor scale is shown on the right hand side of the psychrometric chart. So on right hand side we can see sensible heat scale. So cooling and dehumidification, this process is generally used in summer air conditioning to cool and dehumidifying the air. The air is passed over a cooling coil or through a cold water spray. In this process, dry bulb temperature decreases, specific humidity decreases, and final relative humidity of the air is generally higher than that of entering air. So that is, dehumidification of air is only possible when the effective surface temperature of the cooling coil TF4 is less than the dew point temperature of the entering air. So that is TDP1. So the effective surface temperature of the coil is known as apparatus dew point. So that is the ADP, apparatus dew point. So here you can see the point A. So this is the TA1 and TA2, TA1 and TA2, and this is the point 1 and point 2. And when you extend that, it will be the saturation line is met at point 4. And now this is point, when we draw the line, vertical line and a horizontal line. So this point is A, so that is the HA. So that is the apparatus dew point. It becomes apparatus dew point. So now the dry bulb temperature here, the ADP. So this point is known as ADP, apparatus dew point, and this is point 2 and this is point 1, and we are getting specific humidity on y-axis. So now TA4 equal to TADP. So that is the apparatus dew point temperature, and enthalpy can be find out from this scale. So here the process is shown in figure in earlier slide, and TA1 equal to dry bulb temperature of air entering the coil. TDP1 is dew point temperature of entering air at TX3, and TA4 is effective surface temperature or ADP of the coil. So bypass factor for cooling and dehumidification by BPF is given by the TA2 minus TA4 divided by TA1 minus TA4. So that is nothing but TA4 equal to ADP, and just replace TA4 with ADP, or BPF equal to W2 minus W4 divided by W1 minus W4, that is equal to H2 minus H4 divided by H1 minus H4. So total heat removal during cooling and dehumidification. So actually the cooling and dehumidification process follows the dotted curve shown in figure A. So in earlier diagram, and but for calculations the process is assumed to follow a straight line joining points 1 and A to 2, that is the cooling and dehumidification process. The total heat removed is equal to Q equal to H1 minus H2. So that is H1 minus H4 plus H4 minus H2. So that is latent heat plus sensible heat. So LH, latent heat, is equal to H1 minus H4, and SH equal to H4 minus H2. So that is sensible heat removed. Sensible heat factor during cooling process. So we know that SHF equal to SH divided by LH plus SH. So that is H4 minus H2 divided by H1 minus H2. So now from line 1 to 4, the joining point of entering air and apparatus dew point in figure B is known as the bypass factor line. So that is the bypass factor line, and we will see the numericals on this. So here in this example, in a cooling application, moist air enters a refrigeration coil at the rate of 100 kg of dry air per minute at 35 degrees Celsius and 50% relative humidity. The apparatus dew point ADP is 5%, 5 degrees Celsius, and bypass factor is 0.15. Determine the outlet state of moist air and the cooling capacity of coil in tonnage of refrigeration. So given data, MA equal to 100 kg per minute. So TA1 equal to 35 degrees Celsius, Phi1 equal to 50%, and ADP equal to 5 degrees Celsius, BPF equal to 0.15. So outlet state of moist air. So mark initial conditions 35 degrees Celsius and 50% relative humidity on psychrometric chart in figure. From psychrometric chart, TDP1 equal to 23 degrees Celsius. Since ADP is less than TDP1, it is a process of cooling and dehumidification. Using bypass factor BPF, TA2 minus ADP divided by TA1 minus ADP. So here this is the 1 to A and A to 2, and this is 1 to 2. So this is 1 to 2, and now once you extend this up to saturation line, you will get ADP. So that is 0.5. So this is the psychrometric chart. So substituting these values, we get Ta2 equal to 9.5 degrees Celsius, and from psychrometric chart phi2 equal to 99 percentage. So that is relative humidity at point 2, and cooling capacity of coil from psychrometric chart enthalpy at point 1. So H1 equal to 81 kilojoules per kg of dry air. So enthalpy at point 2 H2 equal to 28 kilojoules per kg of dry air. So cooling capacity equal to MA H1 minus H2 100 into 81 minus 28, so that is 5300 kilojoules per minute. So since 1 tonnage of refrigeration equal to 210 kilojoules per minute, so cooling capacity in TR equal to 5300 divided by 210, so that is 25.24 tonnage of refrigeration. So this is another answer. So next example, 39.6 meter cube per minute of mixture of recirculated room air and outdoor air enters a cooling coil at 31 degree Celsius dry bulb temperature and 18.5 degrees Celsius wet bulb temperature. The effective surface temperature ADP of the coil is 4.4 degrees Celsius. The surface area of the coil is such that it can provide 12.5 kilowatt of refrigeration with the given entering air state. So determine the dry and wet bulb temperatures of air leaving the coil and bypass factor. So we have to find BPF also. So V1 equal to 39.6. So this is the given data, and TA1 equal to 31 degrees Celsius, TW1 equal to 18.5 degrees Celsius, and ADP equal to TA4 equal to 4.4 degrees Celsius, and Q equal to 12.5 kilowatt equal to 12.5 into 6750 kilojoules per minute. Dry and wet bulb temperature of air leaving the coil. So let Ta2 equal to dry bulb temperature of air leaving the coil, Tw2 equal to wet bulb temperature of air leaving the coil. From the psychrometric chart, we find H1 equal to 52.5 kilojoules per kg of dry air, and enthalpy at point 4 ADP H4 equal to 17.7 kilojoules per kg of dry air, and specific humidity at point 1 W1 equal to 0.0082 kg per kg of dry air, and specific humidity at point 4, so that is W4 equal to 0.00525 kg of dry air. Specific volume at point 1 Vs1 equal to 0.872 meter cube per kg of dry air. So mass flow rate of dry air equal to MA V1 by Vs1, so that is equal to 39.6. So 0.872 equal to 44.41 kg per minute. So cooling capacity of coil equal to Q equal to MA H1 minus H2, H1 minus H2 equal to Q by MA. So that is equal to 12.5 into 60 divided by 44.41 equal to 16.89 kilojoules per kg of dry air. So H2 equal to H1 minus 16.89, so 52.5 minus 16.89, 35.61 kilojoules per kg of dry air. So specific humidity at outlet using W2 minus W4 divided by W1 minus W4 equal to H2 minus H4, H1 minus H4, and W2 can be found out. So that is equal to the 0.00677 kg per kg of dry air. So that is W2 specific humidity at point 2. So next example, atmospheric air at 30 degree Celsius dry bulb temperature and 75% of RH enters a cooling coil at 200 meter cube per minute. Coil dew point temperature equal to 14 degrees Celsius, bypass factor equal to 0.1. Determine the temperature of air leaving the coil, cooling capacity of coil in tons of refrigeration TR and kilowatt. So amount of water vapor removed per minute, sensible heat factor. So we have to find these four factors, and the given data is TA1 is given, pi1 is 75%, V1 equal to 200 meter cube per minute, ADP equal to TA4, so that is 14 degrees Celsius. So BPF is also given, so that is 0.1. And now we can find this through this psychrometric chart. So as usual, from 1 to 2, extend that to 4, you will get ADP. And temperature of air leaving the coil from psychrometric chart, TDP1 equal to 25.2 degrees Celsius. Since ADP is less than TDP1, cooling and dehumidification occurs using bypass factor. So now we know BPF. From BPF we can find TA2. So TA2 is equal to 15.6 degrees Celsius. So cooling capacity of coil from psychrometric chart, specific humidity at entering point W1 equal to 0.0202 kg of dry air. Specific humidity at leaving air W2 equal to 0.011 kg of dry air. So specific volume equal to Vs1 equal to 0.884 meter cube per kg of dry air. So enthalpy values H1 equal to 82, HA equal to 58 and H2 equal to 43.5 kilojoules per kg, and mass flow rate can be found out by Vs1 divided by V1 divided by Vs1, so that becomes 226.2 kg per minute. So cooling capacity equal to MA H1 minus H2, so that is equal to the 8709 kilojoules per minute. So then cooling capacity in terms of tonnage of refrigeration, so that is equal to 41.5, and cooling capacity in kilowatts, so 8709 divided by 60, so that is equal to 145.15. Amount of water vapor removed, so water vapor removed equal to MA W1 minus W2, so that is 2.08 kg per minute, and the sensible heat factor is SHF equal to SHF. We know all these values directly, we can substitute and get 0.377 is the answer. So that is sensible heat factor. So next example, moist air enters a refrigeration coil at 35 degree Celsius, dry bulb temperature and 55% relative humidity at a rate of 100 meter cube per minute. The barometric pressure is 1.013 bar. The air leaves at 27 degrees Celsius. Calculate the tons of refrigeration required and the final relative humidity. So the first case is when air leaves at 27 degrees Celsius, TA1 equal to 35 degrees Celsius, pi 1 relative humidity equal to 55%, V1 equal to 100 meter cube per minute, PB equal to 1.013 bar, TA2 equal to 27 degrees Celsius, and this is the complete picture. And dry bulb temperature versus specific humidity for case 1, and this is for case 2, and extending this 1 to 2, we get ADP here. So tons of refrigeration required. So mark initial condition 35 degrees Celsius and 55 degrees Celsius. So 35 and 55. So now this is 55% of RH. So this is 35 and 55. So in both diagrams. Next, from psychrometric chart, TDP1 equal to 24.3. So 24.3 can be found out from psychrometric chart, and TA2 equal to 27 degrees Celsius. So which is greater than TDP1. No dehumidification, only sensible cooling. So from psychrometric chart, H1 equal to 85.4 kilojoules per kg of dry air, and specific volume Vs1 equal to 0.9 meter cube per kg of dry air. So this we can find out from psychrometric chart. Enthalpy at point 2, H2 equal to 77 kilojoules per kg of dry air. Mass flow rate MA equal to V1 divided by Vs1 equal to 100 divided by 0.9. So 111.1 kg per minute. So tons of refrigeration Q equal to MA H1 minus H2 equal to 111.1, 85.4 minus 77 equal to 933.24 kilojoules per minute. So TR equal to 933.24 divided by 210 equal to 4.44. So final relative humidity from psychrometric chart phi2 equal to 86%. And if surface temperature of coil is 10 degrees Celsius, so we know the BPF equal to 0.1, ADP will be 10 degrees Celsius. Now it is cooling and dehumidification process. So psychrometric chart, so reference is the figure. Now bypass factor equation BPF equal to TA2 minus ADP divided by TA1 minus ADP. So then we can find out TA2, so that is 12.5 degrees Celsius, and TA2 equal to 12.5 degrees Celsius, and tons of refrigeration required. From psychrometric chart, enthalpy at point 2 H2 equal to 35 kilojoules per kg of dry air. So thus Q equal to MA H1 minus H2. So 111.1 85.4 minus 35, so 5600 kilojoules per minute, and TR equal to 5600 divided by 210, it is 26.7. So condensate flow, the specific humidity at entering point 1 W1 equal to 0.0196 kg per kg of dry air. So specific humidity at leaving point 2 is W2 0.0088 kg of dry air. The condensate flow equal to MA W1 minus W2, so that is 1.2 kg per minute. So cooling with adiabatic humidification, when air is passed through an insulated chamber air washer having sprays of water at a temperature TF maintained lower than the dry bulb temperature TA1 of entering air but higher than the dew point temperature TDP1, the air is said to be cooled and humidified. No heat is supplied or rejected. Same water is recirculated. This process is known as adiabatic saturation. So this is the temperature of spray water reaches the thermodynamic wet bulb temperature at the entering air. This process is shown in line 1 to 3 on the psychrometric chart in figure. It follows a path along a constant wet bulb temperature line or constant enthalpy line. So this is the diagram, and the psychrometric process, air is in, and this is the spray nozzle humidification process, and it is insulated chamber and air is out, and the pump is used to spray water to pump the water, and this is the makeup water, and here the cyclic process taking place. So this is the T1 equal to TW, and here W1 W2 W3 for the corresponding TD1, TD2, TW1 and TD3. So TD3 and TW1 becomes equal. So this is the psychrometric chart of specific versus the dry bulb temperature versus specific humidity chart. For ideal case, when humidification is perfect, humidifying efficiency equal to 100%, the final air condition is at point 3, the TA3 equal to TW1 wet bulb temperature, relative humidity equal to 100 degrees Celsius, 100%. In actual practice, the perfect humidification is never achieved. So final outlet condition is at point 2 and line 1 to 3, so that is figure B, and important relationship is if length 2 to 3 and length 1 to 3 are considered, length 2 to 3 divided by length 1 to 3 equal to BPF, so that is equal to 0.1. Effectiveness or humidifying efficiency of spray chamber. So the definition is very simple. Effectiveness or humidifying efficiency is given by the actual drop in dBT, dry bulb temperature, divided by ideal drop in dBT. So that is equal to actual drop in specific humidity divided by ideal drop in specific humidity. So then the efficiency efficiency of humidification is equal to, so W1 minus W2 divided by W3 minus W1. Otherwise, in terms of temperature also we can write Ta1 minus Ta2 divided by Ta1 minus Ta3. So Ta1 is the dry bulb temperature at entering air, Ta2 is dry bulb temperature at leaving air, Ta3 is wet bulb temperature of entering air. W1, W2, W3 are specific humidities at point 1, 2 and 3 respectively. So special cases, case 1, when spray water is cooler than wet bulb temperature. If spray water temperature Tf is lower than Tw1, then cooling spray water before pumping to spray nozzles. So ideal process follows 1, 2, 3 as shown in figure B. So in this case, so the efficiency, humidification efficiency is equal to W2 minus W1 divided by W3 dash minus W1. So Ta3 dash and W3 dash, they represent final ideal wet bulb conditions. When spray water is heated, if spray water is maintained at a temperature higher than the wet bulb temperature but lower than the dry bulb temperature, then the process again follows line 1, 2, 3 dash. Efficiency equation remains the same. So the efficiency equation is same as the this only. So here the condition is perfect humidification, then line 1, 2, 3. So the efficiency of humidification is given as like this, and spray water and cooler are heated. So line 1, 2, 3, the efficiency of humidification is equal to Ta1 minus Ta2 divided by Ta1 minus Ta3 dash. So this is the difference, and for these two conditions you have to remember these efficiency equations. So cooling and humidification by water injection, so that is evaporative cooling. So this is also known as evaporative cooling. So water at a temperature Ti is injected into the flowing stream of dry air as shown in figure. So the final condition of air depends upon the amount of water evaporation. If water is injected at a temperature equal to the wet bulb temperature of the entering air Tw1, the process follows the path of constant wet bulb temperature line as shown by line 1 to 2 in figure B. So the water air in is MA, so air out, so that is water MW, that is psychrometric process. So here the specific humidity and the psychrometric chart is TA1 and TA2. So this is 1 and 2, and TW1 is equal to TW2, that is wet bulb temperature. So process analysis, mass balance, MW equal to mass of water supplied, MA is mass of dry air, W1 equal to specific humidity of entering air, W2 is specific humidity of leaving air, HW equal to enthalpy of water injected into the air. So then W2 equal to W1 plus MW divided by MA. So that is heat balance. For energy conservation, H2 equal to H1 plus MW by MA, that into HW. So H2 equal to H1 plus W2 minus W1 into HW, where H1 and H2 enthalpies of entering and leaving air, HW equal to enthalpy of injected water. So the important point here is, since W2 minus W1 into HW is very small compared to H1, and H2 is neglected, so H2 can be neglected here. Thus the water injection process is considered as constant enthalpy process, irrespective of whether T1 is less than Tw1 or Ti is less than Tw1, sorry, greater than Tw1. So we see numericals on this. 200 meter cube of air per minute is passed through the adiabatic humidifier Initial air condition 40 degrees Celsius dry bulb and 15% relative humidity. Final outlet condition 25 degree Celsius dry bulb, 20 degrees Celsius wet bulb. Find dew point temperature, amount of water vapor added per minute. So the given data is V1 equal to 200 meter cube per minute, TA1 equal to 40 degrees Celsius, Phi1 equal to 15%, TA2 equal to 25 degrees Celsius, and TW2 is 20 degrees Celsius. And now dew point temperature is mark initial condition at 40 degrees Celsius and 15% relative humidity at point 1 on psychrometric chart. So draw a horizontal line through point 2 to the saturation curve. So here this is the point 1 to 2, and extend this, you will get the saturation curve, and this is the 20 degrees Celsius. From the chart, so TDP equal to 17.6 degree Celsius. Amount of water vapor added per minute is equal to Vs1, that is 0.896 meter cube per kg of dry air, and specific humidity W1 equal to 0.007 kg of dry air, and specific humidity at point 2 equal to W2 equal to 0.0126 kg of dry air. Mass flow rate of air MA equal to V1 divided by Vs1 equal to 200 divided by 0.896223.2 kg per minute. And water vapor added is water added equal to MA W2 minus W1, and that is equal to 1.25 kg per minute. So next example, a drying room is maintained at 32 degrees Celsius and 30% of relative humidity. The sensible heat gain is equal to 1,50,000 kilojoules per kg. So moisture evaporation, that is equal to 18 kg per hour. If no direct heat source is available, calculate the state and rate of supply air at 15 degrees Celsius dry bulb temperature. So given data is TA2 is 32 degrees Celsius and Phi2 equal to 30% and RSH equal to 1,50,000 kilojoules per kg, MW equal to 18 kg per hour, TA1 equal to 15 degrees Celsius, Cp equal to 1.005 kilojoules per kg degree Celsius. So dry bulb temperature is 1 to 2. So now the 15 and 32 is given. So now the corresponding W1 and W2 and relative humidity is 30%, and the psychrometric chart point 1 and point 2 to be marked, and the mass of supply air. So using sensible heat balance, so that is the RSH equal to MACP TA2 minus TA1. So thus the MA equal to 1,50,000 divided by 1.005 divided by into 32 minus 15. MA equal to 1,50,000 divided by 17.085. It is 8,780 kg per hour. So the specific humidity at point 2 is W2 is 0.0088 kg of dry air, and W2 is W1 plus MW divided by MA. So W1 equal to W2 minus MW by MA. W1 is equal to 0.0088 minus 18 divided by 8,780. So that is coming as 0.00675 kg of dry air. And relative humidity at 15 degrees Celsius. So Pi1 from the chart, it can be found out 65%. So next example is the determine the final dry bulb temperature and relative humidity of air entering an air washer. So given as TA1 equal to 35 degrees Celsius, Pi1 equal to 50%. So that is efficiency equal to 85%. So from psychrometric chart, TW1 equal to 26.1 degree Celsius So the humidification efficiency equal to TA1 minus TA2 divided by TA1 minus TW1. So then the 0.85 equal to 35 minus TA2 divided by 35 minus 26.1. So this is TA2 and this is TA1 equal to 35 degrees Celsius and TA3 it is unknown. And from here W1 and W2 at relative humidity 50% we are getting 0.1, and from here we can find out the TW1 as 26.1, and with that we can find out TA2 value. So TA2 is coming as 27.435 degrees Celsius. So from psychrometric chart, phi 2 equal to 90%. Next example. So air at 30 degrees Celsius and 40% RH, that is the relative humidity, is cooled with a humidifying efficiency of 0.9. So find the specific humidity, dew point temperature, wet bulb temperature. The given data is TA1 equal to 30 degrees Celsius, phi1 equal to 40%, and the efficiency equal to 0.9. So the psychrometric chart we have this, and dp1 can be find out, w1 can be find out, and tw1 can be find out from psychrometric chart. And final dry bulb temperature, once we know this three we can find out ta2. So substituting those values we are getting 20.82 as ta2 value, and this is the psychrometric chart. And this is 30 degrees Celsius ta1, and the corresponding RH is 40%. So from here the TA2 can be find out. So TA2, then the dew point TDP2 can be find out from psychrometric chart. It is 19.4 degrees Celsius. Then example in water injection process. Atmospheric air at 40 degrees Celsius dry bulb and 18 degrees Celsius wet bulb temperature, 100 meter cube per minute air flow. So water injected at 18 degrees Celsius at 48 kg per hour. So determine specific humidity, enthalpy of leaving air, dry bulb temperature, wet bulb temperature, relative humidity. So this is the given data. TA1 equal to 40 degrees Celsius, TW1 equal to 18 degrees Celsius, V1 equal to 100 meter cube per minute, MW equal to 48 kg per hour. So this is the 40 is TA1 is given and TA2 is unknown, and from TA1 draw to this pi 2, this is the point 2. So TW1 is 18 degrees Celsius. So TW1 is 18, wet bulb temperature is 18 degrees Celsius. So once we draw this, now this will intersect at point 2. So there we can find TA2 and phi 2. From psychrometric chart, Vs1 is equal to 0.89 meter cube per kg, and specific humidity at point 1, 0.004 kg of dry air. So enthalpy at point 1, H1 equal to 51 kilojoules per kg of dry air. So mass flow rate MA equal to 100 divided by 0.89, that is equal to 112.4 kg per minute. Specific humidity after water injection, so that is W2 equal to, we can find out, we know all the values. So it comes as 0.0111 kg per kg of dry air. So TF equal to TW1 equal to 18 degrees Celsius constant enthalpy process, and H2 is equal to H1 because it is constant enthalpy process, the water injection process. So it comes as 51 kilojoules per kg of dry air. So now final conditions are the dry bulb temperature TA2 equal to 22.4 degrees Celsius, wet bulb temperature equal to 18 degrees Celsius, relative humidity equal to 65%. So these are the final answers for this question, and there ends the part 2 of this topic, and we will start part 3 in next session, students. You can refer RS Kurmi. I have taken this content from RS Kurmi, and you can refer CP Arora, RK Rajput also for additional problems and information. I prefer RS Kurmi in this particular topic, so please refer that. We stop here, students, and we will see the part 3 of this topic in next session, and we have mixing of year streams, so that we'll see in one more session. In two more sessions we are going to complete unit 4. Thank you, students.